Welcome to the CLearn Security video training lesson. In this video, we will see how to use Nmap and hping in order to perform advanced port scanning. Advanced port scanning techniques include methods to bypass firewalls, perform stealthier scans, have more accurate results, and much more. For our first example, we will deal with a popular technique called IP fragmentation. Fragmentation is a method used in computer networks to split large datagrams into chunks in order to fit the size of a certain transmission link. It is up to the receiving host to reassemble the chunk received into the original packet. IP fragmentation can be used to bypass or create difficulties for some IDS to detect what is happening. Indeed, if the IDS does not apply the necessary rules to reassemble and analyze the whole packet, the fragmented scan may not be identified. Before running our first fragment scan, let's set up Wireshark to listen for traffic in the network. This allows us to intercept the communications between our machine and the target machine. Now that Wireshark is up and running, let's run a simple scan. We do this by watching the differences between the two, and that will make it easier for us to understand the way packet fragmentation works. In the terminal, let's use Nmap to perform a simple SYN scan against a target IP. At the same time, since we want to limit the traffic output, we add the "-PN, the disable ARP ping argument, and the "-N option. Moreover, for the same reason, only port 80 is specified. From Wireshark, we can now see a normal TCP SYN scan. We send the SYN packets normally, and then we receive the SYN ACK packets. Let's now see the differences while using fragmentation. In order to use fragmentation with Nmap, we have to specify the "-F parameter. It will force fragmented packets into a fixed size. Moreover, we also specify the target to scan. For the scan purposes, we choose a specific port to use and also disable ping probes, ARP pings, and DNS host discovery. This will help us better understand how fragmentation works, as we will not have any extra packets displayed on Wireshark. We can now observe the packets on Wireshark. As we can see, the first two packets are fragmented. The default fragmentation of the header is displayed on the first two packets, while our SYN scan takes place on the third packet. Moreover, we can also see the differences from the first two packets, which are the packets sent during the normal port scanning. Let's now take a look at the structure of the fragmented packet. By looking at the packet details, we can see that it defines TCP as the protocol to use. Here, 6 is the protocol number associated to TCP. The offset and the ID above it are used by the receiving host to understand how to reassemble the entire packet. Moreover, if we check the IP flags, we can see that the More Fragments flag is set. This flag is set for all the datagrams except the last one and tells the receiving host to wait for other fragments and then reassemble the packet. As we can see, the fragments are reassembled in the third packet of the fragmented communication. Indeed, the third fragment is our TCP SYN packet destined to port 80. Let's now see what the packets will look like while specifying more ports. We use the same command as before, but we add a few more ports. After executing the command, we can see in Wireshark all the fragmented packets sent, and after them, we can notice the reassembled TCP SYN scan. By default, the fragment scan with Nmap adds 0 data as a payload on the IP header. Thus, we can only see 2 fragments. If we need to break the packet into more fragments, we can use the "-data -length option in order to add some data on the payload of the packet. For example, if we add 100 extra bytes to our payload, we will see more fragments on the Wireshark network. This happens because Nmap tries to split the header into 8-byte fragments, so more bytes will cause more fragments. Indeed, after the scan execution, we can see many more fragments have been sent. Let's explain it even more. First, let's change the data length sent by Nmap to 48. It's a random number to help us understand how fragmentation works. If we do it and execute our scan, we can see from Wireshark that the final packet, after reassembling, has the value of 72 bytes. As we mentioned previously, Nmap splits a packet in fragments of 8 bytes, so normally, if everything went as expected, we should have sent 9 fragments. 9 is calculated by dividing 72 with 8. 72 is the final packet size while, as mentioned previously, 8 is the length of every fragment. By counting the fragments on Wireshark, we can see that indeed we have 9 fragments including the final TCP packet. If you notice on the left number column, you will see that the packets begin from number 16 all the way through 24, which gives us 9 packets. This will help you customize the packets to be transmitted. More fragments may hide our scan from the IDS or the firewall. Another final thing we can do in order to manipulate the fragment size is to add a second -f argument on Nmap. This will cause the fragment to become 16 bytes instead of 8. As a normal TCP packet with Nmap has the length of 24 bytes, the specified scan will only split the packet into one fragment. 16 bytes out of 24 will be associated to the IP header, while the remaining 8 will go to the TCP SYN packet. HPing also provides packet fragmentation. The default fragment length is 16 bytes, so a simple TCP SYN scan will only require one fragment. Let's see an example. As we can see from Wireshark, only one fragment was created. As fragmentation scans have been around for many years, they're more likely to be detected in updated and well-configured firewalls. Thus, other techniques are mostly used now to evade firewalls and IDS. One of them is by using decoys. This scanning option allows us to perform a port scan, but at the same time, flood the IDS logs with useless data. This is possible because we will spoof other machines' addresses and perform fake port scans with their address. All we will do is choose some alive systems on the network and perform a port scan by spoofing their IP address. As we'll not be able to observe the responses to the spoofed IPs, we'll also perform a port scan from our real IP. This technique will help us hide our real IP within the traffic of the other spoofed machines. Let's see how the scanning technique works on Nmap and observe its behavior with Wireshark. To execute the scan, we have to specify the -D option followed by the IP address we will use. It's recommended to add our real IP in the middle of the IP list in order to avoid being detected by the IDS or firewall. Notice that we can use the keyword me to place our real IP address in a specific position on the list. If we don't use the keyword me, Nmap will use IP addresses in a random position. Also, keep in mind that a TCP SYN scan will be used as an example and that we will scan only the most common ports. Feel free to perform these scans against whole port ranges when scanning, and use the variety of the Nmap and HPing scanning options. For the decoy scan, though, it's important to remember that they do not work with TCP Connect Scan and OS Detection Scan. As we can see from Wireshark, we have 4 TCP SYN packets sent from the spoofed IP addresses and from our IP address. We can notice that our real IP is in the middle of the scan, which makes it harder for a firewall or IDS to find out which is the real address that is running the scan. We can also generate random decoys even though they don't exist in the network. To do this, we can use the rnd command, followed by the number of decoys we want to use. From Wireshark, we can see that 10 random IP addresses seem to perform a TCP SYN scan against the target. Among them, we can see our real IP too. HPing, on the other hand, offers something similar. The option --rand--source is the argument we have to use in order to execute the scan from random IP addresses. Here, we also want to specify the TCP SYN scan and the port to probe in order to minimize the output on Wireshark. From Wireshark, we can see that indeed a random IP address is performing the TCP SYN scans on our behalf. The problem here is that modern networks apply filters to limit attacks that use fake IP addresses to perform port scans. For this reason, we can choose to use an IP address for an alive host in the network. With HPing, we can do this by adding the -A or --" spoof option followed by the IP address we would like to use. With this command, we force a TCP SYN scan on port 80, spoofing the IP address of one of the machines in the network. From the Wireshark output, we can see that the spoofed IP address is sending TCP SYN packets to the target machine. Keep in mind that the replies are not displayed as they are going to be the spoofed address. Using decoys to perform a port scan may be very useful. Decoy scan is a method mostly used for identifying hiding. Other techniques, though, are also available in order to exploit certain specific configuration or firewall rules. A very popular mistake administrators do is to allow traffic from specific ports without checking whether this traffic contains malicious requests, port scans, and more. The most interesting thing that will help us understand its severity is that DNS is allowed on almost every network, and sometimes traffic via DNS is not filtered. Therefore, port scan executed with the source port set to 53, the default DNS port, might pass unnoticed. Let's see an example with Nmap. To specify a different source port, we have to enable the --source port option, followed by the port we would like to use. Here, we will use port 53 in order to scan a local target machine. After a couple of seconds, by using port 53 as the source port of our scan, we can successfully see the open ports on the system. From Wireshark, we can indeed see that all of our requests are coming from the DNS port. In hping, we can perform the same action by using the -s or -base port option, followed by the port we want to use. In this case, port 53. Here, we also set the scanning port range in order to scan only the most known ports. Again, with Wireshark, we can see all the TCP SYN packets sent from our IP port 53 destined to the target machine. Another very popular method to bypass firewall filters is to append random data into a packet's header. As many firewalls look at the packet length in order to identify a network port scan, this technique may be useful to bypass some rules. To do this with Nmap, we have to use an option we saw previously when we were working with fragmentation. The option we will use is data length, which allows us to edit the size of the datagram. Now, we will use the same techniques to add some random data inside the header payload. If we're lucky, this will be enough to bypass misconfigured firewalls that check the packet size to detect port scans. With this command, we will add 10 extra bytes into our packet header and forward the TCP SYN packet to port 21. From Wireshark, we can see the appended data on the TCP header. This is random data and will be different every time we execute a new scan. hping also has the capability to add random data into the header payload. We have to specify the ---- data argument, followed by the data size we would like to append in our packet. Here, we also specify the scan type we would like to use, and for the purposes of this example, we also add a specific port to scan, 21 for FTP. In Wireshark, we can see the small difference between data sent by Nmap and hping. As you can see, hping appends fixed data on the packet. It will append several X until it becomes as long as the data length specified in the command. Another popular technique that we can use to avoid firewall detection is the MAC address spoofing. This will help us in configuration where the firewall has a MAC filtering option and either blocks our MAC or accepts only packets from specific MAC addresses. Nmap has 3 subcategories for MAC spoofing. The first one gives us the ability to use the MAC from popular vendors like Dell, Apple, and so on. The second will produce a completely random MAC address for our request, while the third one will let us manually specify the MAC. For all those subcategories, though, we have to specify the --spoof -MAC option. In our first test, we'll see how to choose a vendor's MAC. Once again, we'll use a TCP SYN scan, and then we'll use the MAC spoofing argument followed by the vendor's name we want to use, Apple in this case. We can see from both Nmap and Wireshark that the source MAC addresses belong to an Apple computer. To specify a random MAC, we have to change the vendor's name with the number 0. As we can see, the MAC has been changed successfully to a random one that does not belong to any vendor. If we want to change a MAC address to something specific, we have to replace 0 with the address we would like to use. Keep in mind that a valid MAC address is 6 sets of 2 digits or characters, separated by colons. With this command, we are changing our MAC to the following one. From Wireshark, we can see that the MAC address has been successfully changed. Unfortunately, MAC spoofing is not supported from HPing. Another useful technique that we can use to run a less obvious scan is to randomize the host during the scan. With this option, we can randomly scan an IP range rather than scanning all the IP addresses in sequence. With Nmap, such scans can be executed by adding the --randomize hosts. Moreover, to make this scanning method more clear, we'll create a list with some hosts that are either alive and some that are not. First, we open a file named hosts.list, and we insert 4 IP addresses. After saving the file, we instruct Nmap to read this list with the -I command. Let's also send a TCP SYN scan against ports 80, 443, 135, 5555, 21, and 22. Finally, we add the --randomize hosts in order to randomize the scanning hosts. Once we run the scan, let's inspect the traffic with Wireshark. Here we can see that the host scanning sequence is randomized, while only 2 of the listed hosts are alive. This technique will have better results while scanning the targets with higher delay. Adding a delay on the port scanning will make our scan stealthier, as it will likely avoid alerting the firewall and the scanning logs will be lost among other logs. To add a delay on Nmap scans, we can add the -T option. The accepted values go from 0 to 5. The lower the number, the slower the scan. To perform a slow scan and also randomize the hosts, we will use the previous command and we will add -T at the end. This command uses the previous list and enables a randomized TCP SYN scan against port 80, 135, 444, 555, 21, and 22. At the same time, it uses a timing template of 2, which will slow down the scan. As you can see, the time difference from the previous scan is obvious. It's much slower, but at the same time stealthier. We're going to fast forward the video, but as you can see at the end of the results, the whole scan took 33 seconds. On the other hand, we can use hping for similar actions. Hping has an argument called randdest, and we can use it to randomize the hosts to scan. Like Nmap, hping will scan some given hosts in a random sequence. For example, to determine which hosts are up by randomizing the requests, we have to do something like this. This command uses the -rand-dest option to force the random host scanning sequence, while the X at the end of the IP tells hping that the random range to scan is the last 8 bytes of the IP and thus 256 hosts starting from 192.168.1.0 until 192.168.1.255. The -1 parameter enables the ICMP probes, and the -I is a mandatory parameter which specifies the interface we would like to use. As this scan may take a while, we will pause it for the purpose of this video. We are also able to specify the time delay between the probes. To do this, we can add the -I parameter followed by the number of seconds that hping has to wait between each packets, or use the letter U followed by the number of microseconds between each packet. In this case, we want to run a very fast scan, and we will instruct hping to perform a scan with 10 microseconds of delay. What we've seen until now are the most common techniques available for firewall bypassing and stealthy port scanning. Feel free to improve the commands by combining the above methods. We highly encourage you to use Wireshark for every request you send, in order to deeply understand what's going on at the network. Thanks very much for joining us.